Hello everyone, welcome back to my YouTube channel. Today we are going to discuss some problems on positive real function. We have discussed what is a positive real function and how to do problems. I've given you an example on our last class. In today's class we are gonna discuss a more complex question, that is like a polynomial with some higher order. So today we are gonna discuss one question, that is I've written here: check whether the following function is positive real or not, and the function f of x is given here. So as we learned yesterday, we are gonna do some methods, and also since it is a higher order function, we will be doing some additional methods to solve these problems. So first of all, I'm gonna answer this, and the first criteria that I'm gonna check is all coefficients. I'm going to check all coefficients whether they are positive or not, and on checking that I could see all the terms have positive coefficients, right? So I could say all coefficients are positive. So our first criteria is done. Next thing we have to know is whether they are Hurwitz or all the mm, the yeah, I would say second criteria will be to check whether all the roots lie on left half of S-plane. So yesterday we did this by just taking the root directly from the equation, like equating the numerator and denominator to 0. We have found the roots whether they are on the left half of the S-plane or not. But today we are going to do that by doing another kind of equation, that is we are solving the Routh-Hurwitz criterion way. That is, we'll be writing a Routh array from the given function, and we'll check whether all the poles are on the left half of the S-plane. So let me explain how we are going to do this. This criteria is mainly done to check stability. That is, stability actually means whether roots are on left half of S-plane. So I'm going to do Routh-Hurwitz criterion. So first of all, I'm taking the numerator first. Okay, that is s cube plus, I'm writing n of s as s cube plus 6s square plus 7s plus 3. Isn't that it? 6s cube plus 6s square plus 7s plus 3. So now I'm going to solve it. So in a Routh array stability criterion, what we are going to do is we'll be first writing the s of the certain order in a column. So I'm writing s cube first, going down s square, s1, s raised to 1 and s raised to 0. The next thing I'm gonna do is I'm gonna write all the coefficients in these terms in a particular manner, zigzag manner. So first I'm gonna writing the first coefficient, that is 1, and the second coefficient I'm writing just below the first one, that is 6, and the next one I'm gonna write on the next column, so 7 and 3. So this is how you start a Routh array, like we write the coefficient in a zigzag manner. Then the next thing that we are gonna do is we have to find the other terms. So in order to find other terms, what we are gonna do is we are gonna multiply this 6 into 7 minus 1 into 3. What we are going to do is 6 into 7 minus 1 into 3 divided by the value just below it, that is 6, just above it, that is 6. Okay, on doing this we will get the answer as 13 by 3. So what it will look like is this will look like 1763, and our answer 13 by 3. And then there is we can say whether there is a second term. We can check that. Now that we see this, there is no term here or here. If there was any term in these two places, we could have figured an answer for this place. Since there is no such term, so there won't be second term in that row. So we'll consider that term as 0, and we'll move on to our next row. Here what we are going to do is, we are going to do the exact same procedure that we had done earlier. That is, I would do 13 by 3 into 3 minus 6 into 0 divided by 13 by 3. Just as I did earlier, and the answer will be 3 will go cancelled. This will not be there. 13 by 13 will cancel, and the answer will be 3. So what I'll be getting in the end is s cube s square s raised to 1. Actually, you don't have to write it multiple times. You can just solve it in one writing. I'm just doing it because you can understand it a little better. So I'm doing this, and yeah, we got 3 as our last answer. So this is how you solve a Routh array. Next, what we're going to do is, we have to know that the system is stable, or all the roots are on the left half of S-plane. So how will you know that? It is very simple, that if the first column of the Routh array is positive, then all the roots are on the left half of the S-plane, and that means the system is stable. So now that we see this, every term in this Routh array is positive, so we could say the polynomial n of s, that is stable. Next thing we do the same thing with the denominator, that is d of s, that is equal to s square plus 2s plus 1, and I'm gonna solve it like I did earlier. So 1 2 1, and here 0, there is nothing, so I put 0 here. So I'll be solving this. Then how will it look like? It will be 2 into 1 minus 0 by 2, and it will be 1. So what we get is 1 2 1 1. So what's the first row? The first row is all positive. All the elements in the first row is positive, hence this equation is also stable. Now that we have identified that all the roots are on the left half of the S-plane, our second criteria is also satisfied. Then we'll move on to another criteria. Last time we put f of j omega and found out that real of f of j omega is greater than or equal to 0, right? But the question was very simple, like s plus 1 by x plus 2 or something. So we use that method. In this method, the polynomial is of the higher order. As you can see, the polynomial is of higher order. As you can see, the polynomial is of higher order. So what we are going to do is, we are going to do another method. Another method means we check another criteria similar to this one, which is m1 m2 minus n1 n2 greater than or equal to 0, and we'll get to what m1 and m2 is. So basically we know the function, right? F of s is equal to s cube plus 6s square plus 7s plus 3. That's our question. So this function, we take the numerator as the first terms and we take the denominator as the second terms. What I'm going to do is, I'm going to write split this numerator into even and odd and the denominator into even and odd. So I'm writing the even terms m1, that is the even terms from the numerator, that will be 6s square plus 3. And I'm writing the even terms from the denominator. This is from the numerator, this one from the denominator, that is s square plus 1 from the denominator. The same thing I'm repeating. I'm writing odd, that is n1 and n2. n1 is the odd terms of the numerator, that will be s cube plus 7s, and the denominator, in case, okay, I'm writing s cube plus 7s, that is the numerator, and 2s as the denominator. Okay, the odd term of the denominator. Okay, now we have gotten m1, m2, n1 and n2. The next step that we are going to do is, we are going to equate it. It is m1, m2 minus n1, n2. And we're going to solve this equation and find whether it is greater than or equal to 0. So what we're going to do is, I'm going to do m1 into m2 minus n1 into n2. And I'm going to solve this. It will be 6s raised to 4 plus 6s square plus 3s square plus 3 minus 2s raised to 4 plus 14s square. Yeah. Then I'm solving this 4s square minus 5s square plus 3. We'll get this answer is the final. Now what I'm going to do is very simple. I'm going to put s equal to j omega as we did in the earlier question. I'm going to put s equal to j omega and I'm going to solve it. So in this equation, that is m1 m2 minus n1 n2, I'm going to put s equal to j omega, that is j omega the whole raised to, sorry, this is actually s raised to 4. 4 j omega raised to 4 minus 5 j omega the whole square plus 3. Now we'll solve this. We know that j square is equal to minus 1. J raised to 4 will be minus 1 into minus 1, that is 1. So on solving this, we get 4 omega raised to 4 plus 5 omega square plus 3. For whichever value of omega, if we give positive value or a negative value or a 0 value, whichever value we give for omega, the answer will always be greater than or equal to 0. Implies we could say that all our conditions are satisfied. We have checked whether the polynomial, all coefficients are positive, whether the roots lie on the left half of the s-plane, and then we did our, this is basically simply another method to find the real part of f of j omega. We does this method because it is the question is of higher order and it is more simple than doing the other one. So this condition is also satisfied. So we could say that the given function is positive real. So that's all for today. Hope you all understand. Thank you so much for watching. Stay tuned. If you like the videos, please do like and subscribe to my channel. Thank you.